Hello and welcome to lecture number 16. So today we are going to discuss a little bit more detail on the factors that govern the microemulsion structures. So today we will be having our last discussion, our last lecture on the topic of microemulsion. So as you can remember that last time we discussed that there are four major factors that dictates the microemulsion phases. That means whether it would be oil in water microemulsion or water in oil microemulsion. So surfactant choice, electrolytes, temperature, and alcohol. And as I mentioned briefly, that for ionic surfactants, if you have more electrolytes, it would form more into the type 2 Windsor system. And if a non-ionic surfactant forms type 1, then with increasing temperature, it would gradually shift to the type 2 Windsor system. And we already mentioned alcohol had a role, and if we have sufficient amount of alcohol added as an amphiphile with the surfactant, there is a tendency that type 4 Windsor system will be formed. Now in surfactants, we have an option to vary the two things. The number one, depending on the surfactant, the critical packing parameter would change. So this is related to the structure, geometrical structure of the surfactant. And the second factor is the solubility of the surfactant. Okay, so today we are going to discuss briefly the two factors. So we start with the solubility factors. So here I have drawn two different types of microemulsion schematic diagrams. So these are the segments of the emulsion droplets. So this one here, we can define it as water in oil. So let's write water in oil microemulsion. So we can have that droplet. This is the water droplet, and the external phase is oil. Okay. So the polar head group is facing towards the water, and here it is just the reverse. So this side is oil and this side is water. So this is oil in water microemulsion. So now when we add a surfactant, so primarily the factor that would govern whether it is water in oil or oil in water is the solubility. So there is a rule, it's called the Bancroft's rule. Okay. So the Bancroft rule says that the medium where we can write it here, the medium in which the surfactant, in short form I'm writing S, in which the surfactant is more soluble or stable, whatever, that medium will be the external medium. That means outside of that droplets. So here, when water and oil emulsion is formed, we have to assume that the surfactant, whatever I have drawn here, it is more soluble in oil, and here the surfactant is more soluble in water phase. The reason, now you may ask that why it is, it is something like that. Now the answer lies in the free energy or surface tension or interfacial tension. So we can take this segment, right, for this one or this one. We can imagine that these two segments, okay, so this can be represented something like this, all right. So as a curvature. So in the middle, we have the surfactant layer. Okay, so these are the amphiphile, the surfactant S. So here we have the outer curvature, and here we have the inner curvature. Obviously, between outer and inner curvature, the outer curvature will have the higher surface area. So whenever a surfactant is more soluble, so that medium would be losing its interfacial tension more than the other medium where the surfactant is not easily soluble. So therefore, the medium which is losing its surface tension would expand much more compared to the other medium. So therefore, the medium where the surfactant is more stable or more soluble would always stay at the outer uh, region. So that means the droplet would form by taking the medium in which the surfactant is less soluble. All right. So I hope this explains primarily that where we can expect water in oil emulsion or oil in water emulsion. So that means primarily if we have an ionic surfactant like CTAB or dodecyl sulfate. So keeping all other parameters at its normal condition, it is expected that we can have from the solubility rule, of course, we have a oil in water microemulsion because SDs would be expected to be more soluble in water rather than the oil. All right. So next we would move on to the factors that govern the microemulsion phases based on the structural geometry of the surfactant. In other words, critical packing parameter. So let me clean the board and address the critical packing parameter in the context of different phases of microemulsion. Okay. So now we are going to discuss that how critical packing parameter affects the microemulsion phases. So I have drawn some schematic diagrams and written some numbers. So let me explain this gradually. So this ratio V over A naught multiplied by LC, it is nothing but the critical packing parameter as we have learned in the chapter of micelles. So once again, V is the volume of hydrocarbon chain length, A naught is the area of the polar head group, and LC is the critical chain length. All right. So now, if this critical packing parameter becomes smaller, that means a fraction, 1/3 or so, is expected to form some spherical micelle. And whenever it is expected to form spherical micelle, we expect an oil in water microemulsion in the extreme case. And as the critical parameter value increases with smaller head group area and larger V, that means the larger hydrocarbon chain volume, the tendency of forming spherical micelles go into the inverted micelles through biliary vesicles. So at the extreme case, where we have a smallest polar head group area, that means the head group is quite small, but its critical chain volume, that means the hydrocarbon chain volume is very high. That means the surfactants are highly branched, then it is expected to form water in oil microemulsion. All right, and in that situation, we have these critical packing parameter value exceeds 1. So in earlier cases, we learned that if it exceeds 1, we have inverted micelles. So here, this is the situation. And in this region, between 1/3 to 1, we have certain possible structures. So these at these middle portions, these micelles that are formed that may not be spherical but some other structures as predicted by CPC and as I described it earlier. So what I would like to emphasize on that in absence of the oil layer, if we have only water layer, and if we add a surfactant with CPC value 1 by 3, it is expected to form a spherical micelle where inside there is no space. It is absolutely packed. But when we have oil, so when it forms the microemulsion, oil in water microemulsion, so the micelle structure expands and inside there is a hollow space and they incorporate oil. And probably that's how the word solid micelle came. And now it makes sense also because as if it appears that the micellar structure has got swollen to incorporate the oil phase. So and the exactly opposite becomes over here when it forms watery oil microemulsion. So this side we have smaller hydrocarbon chain volume, larger chain critical chain length means that the chain increases in the length, not sidewise. And here we have larger hydrocarbon volume, smaller chain length, smaller compared to the branching. So larger hydrocarbon volume comes from highly branched chains. And also I have included the other parameters in the same diagram. So if we are talking about ionic surfactant, at lower ionic strength we have water in oil. At higher ionic strength we have a tendency to form water in oil, because if we add some extra electrolytes it would try to screen the charge of the ionic polar head group and it would behave kind of non-ionic manner, and we have formation of water in oil. And if we have a non-ionic surfactant, lower temperature would form this, and the higher temperature would basically form this. So in Windsor system, this is more represent. This represents type 1 more closely, and this represents type 2. More closely. The type 2 equilibria, Windsor systems. And then we have pH conditions also. So if we have surfactant, something like this, where the head group is NH3 plus. So this is a cationic surfactant. So at lower pH, when the pH is acidic, is expected to stay as NH3 plus. So at lower pH, cationic surfactant would tend to form oil in water, and also for anionic pH, something like that. At higher pH, that means at basic pH, it is expected to form CO minus. So it will form the oil in water microemulsion. All right. So and also the reverse is true, that if we have higher pH, that means in basic pH, the cationic surfactant will form water in oil, and in lower pH, meaning acidic pH, so the CO minus would like to stay as COH, so it would behave as a non-ionic surfactant, and it has a tendency to form water in oil microemulsion. And there is one more parameter I have written, HLB. So HLB stands for an index. It is called the hydrophilic lipophilic balance. Okay, so that means in a surfactant there is a hydrophilic part, there is a lipophilic part. So the balance between the two. So this HLB is represented something like the hydrophilic factor minus the lipophilic factor plus some constants. So and it expected to give you a positive value. Now higher is the number, means 40 is greater than 20 is greater than 10. So the higher HLB means the hydrophilic part predominates. So here, so the HLB index is represented as hydrophilic part minus the lipophilic part plus there is some number, some integers. Okay, so and some integers. So the integers is usually okay. So some integers. So now, if we have a high positive value, That means the hydrophilic part is much greater than the lipophilic part. Now, if the positive value gets smaller and smaller, the lipophilic part predominates. So now here we see for having a greater HLB number, we have a tendency of water in oil microemulsion, and for a lower HLB number, we have a formation. We have a tendency to form. Yeah, means for a lesser HLB number, we have a tendency to observe water in oil microemulsion. So, if we can try to visualize this chart. You don't like to, means you don't have to memorize it, but if you have an impression of whatever schematic diagram I have drawn here, and if you try to understand the significance of this diagram, then I hope it will be absolutely clear to you that in what kind of surfactants, means the solubility and the structure of surfactants, how those two factors would dictate the types of the microemulsion form, whether it is water in oil or whether it is oil in water. So we are done with the types and factors of microemulsions. Now the next topic is how to study the experimental data when a microemulsion is formed from a specific composition. All right, so let's follow that out here. So uh, adding surfactants at a fairly high concentration in presence of oil gives you microemulsion. So the microemulsion region for a oil, water, and surfactant mixture is determined and plotted on a triangular diagram or a three-phase diagram, and that is known as a ternary diagram. So the utility of such ternary diagram is, suppose you have water, you have oil, and you are adding the surfactant. So if the surfactant doesn't reach at a specific concentration, you may have formation of micelles in water, or you can have the micelles in oil. And then when you have sufficient amount of surfactant, you may form the microemulsion. So it could be type 2, it could be type 1, and if you keep on increasing the surfactant concentration, there could be a different phase, so the phase equilibria changes. So the question is, can we follow the different changes of these phase equilibria with the different or with the change or variation of the concentration of the surfactant. So here you see the parameters are 3 instead of 2. So therefore, to plot a diagram from a varying 3 parameters, it can be best represented by the ternary diagram. So let's take an example and try to draw or try to plot a composition of 50% water. So the composition X, which says that 50% water and we have 25% of surfactant and 25% oil. All right. So here, how to represent this? So a ternary diagram is basically plotted by forming an equilateral triangle. So in one of the axes, we can plot water. So that means here we have 0% water and here we have 100% water. And then we move on. Then we move on to the oil axis. So this is water axis, this is oil axis. So oil axis starts from 0% here, ends at 100% there. And then we have surfactant axis, it starts from 0% here and ends at 100% here. Okay. So in your textbook, you will see that there are some ternary diagrams are given, and in different regions, we have formation of different phases. So can be micellar phase, can be isotropic phase, can be a Windsor type 2 or Windsor type 1, etc. So if you vary water, oil, and surfactant, by different proportion, so you will reach the different phase equilibria. Now the question is how to read it. So two way we can do it. We can start with the known composition and try to draw the try to get the point here, or we can just pick a random point over here and try to find out what percentages of surfactant, water, and oil does this point represent. Okay, so we'll come to that later, maybe. So let's first start with this 50% water, 20%, 25% surfactant and water, oil each. So here, approximately this is the 50% line. Okay, so this is 0, this is 100, 50% of, this is the 50% water. Okay, fine. So then there should be one fixed line along which all the compositions would represent 50% water. Now the question is which should be the line. So remember always we have to draw a line where the line should be opposite to where the 100% water is there, and it should be parallel to the line which is just opposite to this 100% water. So that means we have to draw a line like that. Very good. So this any composition along this line would have 50% water. All right. So next we go to 25% surfactant. So this is the surfactant composition. Okay, so surfactant composition 25% means, so this is 50, so this is approximately, so this is 25%. So we have to draw a line where opposite to the a line parallel to the side opposite to the 100% surfactant. So this line would represent, so this parallel line would represent 25% surfactant. And so these two lines intersect over here. All right. So this line should represent 25% of oil. So let's verify it. So where is my oil axis? So this is my oil axis. So a line parallel to the 100% oil, uh, the line opposite to the 100% oil is this, and the line parallel to this having this composition would be something like this. So along this line anywhere the composition of oil is fixed at 25%. Okay, so here we get, and so this line here, so this is the oil axis. So and I reckon this is 50%, so this should be 25 and this should be 75. So 0, 25%, 50%, 75%, 100%. So this is the oil axis. So that's how we can represent any point, any composition on a ternary diagram. So an exercise for you. So can you represent, suppose we take a point over here. All right. So of course for this you need to have grid lines. So you can draw some imaginary grid lines, and just as a part of an exercise, try to find out the composition represented by this point from the ternary diagram. So please practice it out yourself, and in the exam some questions may come to either pick a composition or draw a point corresponding to a composition on the ternary diagram. So these ternary diagrams are very relevant on this oil water surfactant phase equilibria, and please follow your prescribed textbook for more information and the diagrams. Alright, so we have come to the end of this microemulsion topic. So our last point of discussion is the simple applications of microemulsions in industry. So we will take two examples, each from paint industry, and the second is one from the food industry. So let's discuss it. So lastly, we are going to talk about some industrial application of microemulsion. So there are many applications, but we are only going to talk about two, which is paint first, and the second in food industry. So what is paint? So the purpose of paint is not just to put some color on a surface, but to put a protective coating, which is basically hydrophobic, non-wetting surface. So that protection comes from application of a polymer coating, organic polymer. So there we have to use the emulsion chemistry because this organic polymer is only soluble into organic solvent, and it needs a thick viscous mm, form of the substance to be coated on the walls. So we just can't use the organic solvent to apply the painting because number one, organic solvents are expensive, and number two, think about the fire hazards that come from handling so much of organic solvent. So therefore, the answer is emulsion chemistry. So we have to use a microemulsion of polyacrylics. So all the paints that we basically see or come across, so those are acrylic based paints. So this is actually comes from acrylic acid. By mixing acrylic acid with butyl and butyl acrylate, so these are monomer form. So these are taken in the monomer form. So in situ they actually polymerize. So in a emulsion, this is taken as a 50% ratio, and then 2% of all the substance will have a substance chain terminator, that means the thing that would terminate the polymerization process, plus the surfactant which would disperse the oil in water, and 48% water used as a solvent. So basically this is oil in water microemulsion. So once the painting is done, water gets evaporated and we have the uniform layer of the acrylics or polyacrylics. Now the color. So the color comes from the pigment. Pigment, these are organic substances, and it gives the color. So these pigments actually exist as a colloidal dispersion in the paint medium, and once the water gets evaporated, these pigments get absorbed on those polymer surfaces uniformly, and we have the color paints. So our next example is in food. So the biggest micro emulsion based commercial substance that we see is the ice cream. I mean, these are man-made micro emulsion. So it's again oil in water micro emulsion. So the surfactant is a dairy protein. So the dairy protein coated fat droplets. So surfactant, and this is the oil, means fat serves as the oil layer, and that is dispersed in water. Not just water; it is actually aerated water. Means lots of air bubble are present in the water, and then the major trick for ice cream is that the water has to be frozen in a certain manner that it gives certain fine grains of ice crystal. So the unique taste of ice cream actually comes from that fine grains or the fine texture of this ice crystal. So a lot of engineering is actually happens to get that water crystallized in a certain fashion. So making these the dairy protein coated fat globules dispersed in water is rather trivial, but the most important and tricky part is to form those crystals, because you see once the ice cream is melted and if you want to freeze it again by keeping it in the deep freezer, the ice cream gets frozen back, but you lose the taste. It means it doesn't taste as good as it was before. Why? Because it's the same solid substance, but it still stays as the micro emulsion. The problem is once you melt and refreeze the ice cream, it loses the crystal grains that were present before when you purchased the ice cream. So therefore, the unique taste of ice cream comes from a particular structure of ice crystal. So that has been engineered in the ice cream making factory, which is not possible at home. So therefore, in food industries as well as in paint industries, there are a lot of applications of the microemulsion science. All right, so with this, we finish our chapter of liquid dispersed phase in liquid dispersion medium. So uh, please follow these video lectures, and also please don't forget to follow the textbooks that I have shared with you for the details of these microemulsion chapter. So I will see you in lecture number 17 with some new topic. So till then, goodbye.